Okay, so yesterday and the day before, we have been talking about isotopes. Isotopes are identical elements. So all isotopes are identical. Everything is the same. Their number of protons is the same. Their number of electrons are the same. They have the same properties. They probably react in the same way. The only difference between isotopes is the number of neutrons. So if we are increasing the neutrons, what is getting bigger? The mass number, and where neutrons live? The nucleus. So, for instance, hydrogen has 3 different isotopes. We have hydrogen 1, hydrogen 2, and hydrogen 3. As you look at this table, our protons and electrons are all the same, right? The only thing that's changing is our number of neutrons. So if we look at the nucleus, for hydrogen 1, all in the nucleus is one lonely proton. If we look at hydrogen 2, he finally gets a friend. We have 1 proton and 1 neutron. And then hydrogen 3, there's 3 of them, so we have 1 proton and 2 neutrons. So everything is staying the same except for the number of neutrons. As our neutrons increase, so do our mass, and so does our nucleus. More things shoved into the nucleus makes it more unstable. Okay, so now that we kind of know that, which of these 3 do you think is the most unstable? Hydrogen 3. Okay, which of these 3 do you think is the most abundant? Which one do you think we have the most often? Hydrogen 1. Okay, why? Because 1, it has the smallest nucleus. And then secondly, another way to check your answers is if you look at the periodic table, hydrogen has a mass of 1.00794. Is 1.00794 closer to 1, 2, or 3? 1. So hydrogen 1 is the most abundant. Okay. So, funny thing about isotopes is elements occur in nature as a mixture of isotopes. So if I have a collection of oxygen, which is in the air around us right now, I probably do not have one form of oxygen. It's probably not all oxygen 16. We probably have oxygen 16, 17, and 18 all in a mixture around us. That's what we're breathing. Okay, but isotopes are atoms of the same element that differ in the number of neutrons, so every element has a different number of isotopes. Some have 2 forms, some have 3 forms, some even have 4 different isotopes that can occur. Alright, so what we're getting to today is the atomic mass, which is what is listed up there in the periodic table. So if I ask you how heavy is an atom of oxygen, am I asking you specifically how heavy is 1 atom of oxygen? No. Probably not. I'm not really asking you specifically because it would depend on what oxygen atom. It would depend on if we're dealing with oxygen 16 or 17 or 18 or who knows how many isotopes, right? It would depend. So really when I ask that question, what am I really asking you? On average, right? So when I ask those types of questions, I'm actually asking you the average atomic mass, which is what is listed on the periodic table. It's something called the average atomic mass. And these masses are based on something called abundance. Okay, abundance is a percentage. So for instance, if let's say we have 10 oxygen atoms, 6 of them are oxygen 16, 2 are oxygen 17, and 2 are oxygen 18. My abundance, 60% of it is oxygen 16, right? 20% of it would be oxygen 17, and 20% of it would be 18. So basically, your percent abundance is how likely you are to get that specific isotope. Okay. All right, but so far when we are dealing with mass, we have usually been measuring it in grams. Can we find the mass of atoms in grams? No. Why? Atoms are way too tiny for us to find a mass in grams. So, more specifically, we have to find their mass in... anyone? Close. Corey's close. We have to find it in something called an atomic mass unit. Okay? Instead of grams, we use a unit called the atomic mass unit, which is shorthand as AMU. Well, just like we have a system or a basic to set all of our grams off of, right? We have like a set of weights that tells you exactly what 1 gram is, and we can feel it, and we can see it, and we can weigh it, right? Well, AMU is not exactly the same, right? Because we can't see atoms, so it's a little bit harder. So basically what they did to determine what an atomic mass unit is they took a carbon-12 atom. Carbon-12 is an atom that has 6 protons, 6 neutrons, nice, pretty nucleus. It is very stable. It is very common. It's around you all the time in this room. So what they did is they said, well, this has 12 atoms in the nucleus. So we're going to take a carbon, we're going to divide it by 12, and that is what we are going to define as an atomic mass unit. So basically, if you take carbon, you divide it by 12, that's what an atomic mass unit is. Why did we use carbon? Anyone?
Isotope purity.
Okay, first of all, carbon is very abundant. Like I said, it's everything in this room. Secondly, it's very pure, which means it doesn't get altered very easily. Okay, carbon pretty much maintains its characteristics. Okay, each isotope has its own atomic mass. Therefore, we have to determine its average from its percent abundance. So, when you guys find an average, don't you just take what you got on a test divided by the total number of points? Yes. Okay, we can't really do that the exact same way because we have a whole other thing factored in here. We have to take into account its percent abundance. So it's kind of like our scale, our grading scale. You know how it's weighted? You might have gotten 100% on a practice grade, but is it going to affect your grade very much? No, because that's only 15% of your grade. But if you were to get 100% on a test, is that going to affect your grade? Yes, because it's 65% of your grade. So basically, finding your average atomic mass is basically weighting it based on the percent abundance. It's just like we do our grading scale when we weight assessments versus practice. Okay, so how in the world do we calculate it? Because yes, I'm going to calculate it. First of all, to find the average, you have to take the atomic mass of each isotope and you have to multiply it by its percent abundance. Now, can we do math with a percentage? Do you do math with a percentage? No. In order to do math with a percentage, you have to convert it back to its decimal form. Because when you guys find your percentage, don't you take 12 divided by 20 and don't you then times it by 100? So to actually do math with your abundance, you have to put it back in its decimal form, which means you just move the decimal over twice. Okay, after you have done the mass times the abundance of each isotope, so if you have 3 isotopes, you have to do that 3 times. So once you get your 3 answers, you just add them together. Okay, if not told otherwise, you're going to express your answer in atomic mass units, not grams. So let's think back to significant figures really quick. Because when we're doing this, I always get questions on, well, how do I know how to maintain significant figures? So let me ask you something. Does your mass number affect your significant figures? Why would it not affect your significant figures? Why would your mass number, so again, mass numbers are the numbers written associated with an isotope, right? Why would these not affect your significant figures? There are 2 exceptions to significant figures. Anyone know which one it is? It's kind of both. Remember, the exceptions to significant figures are if it is a counted item or if it is an exactly defined quantity. Isn't the mass number both? It is a counted. They have counted the protons. They have counted the neutrons. And it's an exactly defined quantity because it's on the periodic table. So it actually meets both ways. So is the mass number going to affect your significant figures? No. So you have to look at the other information that you're given. Okay, so let's do an example. So here we have carbon. And I'm going to write on the screen so that it pops up on my video. So here we have carbon. What we're going to do is carbon exists in 3 different isotopes. So in order to figure out my average atomic mass, you have to take your mass times your percent, mass times your percent, mass times your percent, and add them all together because we have 3 isotopes, right? So we have carbon-12 and we have 98.89. So which number is my mass? 12. So I'm going to take 12 times what?
I have to move my decimal twice, right? So I'm going to use the decimal form, not the percent. So I'm going to times it by 0.9889. What am I going to do for carbon 13? 13 times. So I'm going to do it by 0.0111. What am I going to do for 14? 14 times, move the decimal over twice, 0.0001, correct? Then I'm going to put these all in my calculator, and I'm going to get 3 numbers. Now, this is what I'm talking about, significant figures. How many significant figures does carbon 12 answer get to keep? 4, because carbon, the mass number has an unlimited, right? So we are going to have to look at our percentage. So if you take 12 times 0.9889, we get 11.8668 in our calculator. What should I round that to? 11.87. Kind of hard to read, but I think we can do it. Okay. Next step, 13.0111. How many do I get to keep? I get to keep 3. Why do I get to keep 3? Because there are 3 numbers in the percent. So 0.1443 is what my calculator pops up, so I have to round it to 0.144. A little bit easier to read. Okay, then I have to do the next one. So if I do 14 times 0.0001, I get 0.0014. How many do I get to keep? 1, because 0.0001 only has 1. So now I have all of my numbers. What do I have to do now? Add them all together. My significant figure rules change a little bit now, though, don't they? How do my significant figure rules now change? I'm not counting significant figures, I'm counting decimal places. The first number has 2 decimal places, this number has 3, and this number has 3, so how many does my answer get to have? 2. So if you add all of this together, you get 12.01. I think it's 0 over here. I can't remember off the top of my head. But let's see if we're right. .011. Were we right? Yes. Okay, so another way to check to see if your answer is correct, look at the periodic table. Did you get the right answer? The right answers are up there. I'm just showing you how to get to the right answer. Okay, so let's pretend the percent abundances aren't there. I give you the atomic mass and I ask you to rank them. Let's pretend the percent in nature is not there. So is 12.011 closer to 12, 13, or 14? 12. So what's the most abundant? Carbon 12. What's probably next? Carbon 13 followed by 14. So when you are asked to rank things by most abundance, you compare them to the average atomic mass. So let's look at chlorine. Chlorine on the periodic table has a mass of 35.45. Okay, so if we look at chlorine, chlorine's mass is 35.45. So chlorine exists in 2 isotopes. We have chlorine with a mass number of 35, and we have chlorine with a mass number of 36. If I asked you to comment on their percent abundance, what would you say? Chlorine 35 is going to have a bigger percentage because 35.45 is closer to 35, right? So that means chlorine 36 is going to have a smaller percentage, but are they going to be that off from one another? No. If I had to guess, I'd probably say it's probably in the ballpark of, not 45, 55% versus 45%, if I had to guess. We could go through and we could do the math, but if I was just guessing, 35.45, it's going to be a little bit greater than 50%, a little bit less than 50%. So in ballpark.
All right, so let's do another example. This time I don't tell you what element I'm dealing with. We are dealing with element X. Element X has two natural isotopes. The isotope with a mass of 10.012 and it has a percent abundance of 19.91. And then the other isotope has a mass of 11.009 with a relative abundance of 80.09. And it asks you to calculate the percent abundance. Well, if you notice, didn't it give you two more numbers in the problem? It gave you X10 and X11, right? So it gave you the mass number and the mass, correct? So all day long I keep getting the same question. Which number am I supposed to use? Am I supposed to use the mass number or am I supposed to use the mass? So let's think about it logically. Which do you think is going to give you a more accurate number? To use the mass number or to use the actual mass? It'd probably be more accurate to use the actual mass. So if you're given the option, use the actual mass. If you're only given the mass number, then you have to use the mass number. But if you're given the mass, use the mass. Okay? So let's see if we can do this one all by ourselves. So we were given two isotopes. We were given one with a mass of 10.012 and it was 19.91%. We were given another one with a mass of 11.009 with a percent abundance of 80.09. Before we even do the calculation, I want us to guess. What do you think the average atomic mass is going to be based on the percent abundance? Let's just, in the ballpark, let's see if we can figure it out. We have one that's really close to 10 and one that's really close to 11. If it's 80-20% abundance, if we had to guess what our average atomic mass is, what do you think it would be? Probably not 11. Between 10.5 and 11, right? So let's guess 10.75. Let's just guess. That's our guess based on just looking at the data. So now let's do the math. So how do I do this math again? I take what times what? You take mass times percent as a decimal. So I'm going to take 10.012 and I'm going to multiply that by 0.1991. And I'm going to get 1.9933892. How many numbers do I get to keep? 4. So it's going to be 1.993. I have to do the same thing for the other isotope, so I'm going to take 11.009 times it by 0.8009. And I get 8.8171081. I get to keep 4 again, so it's going to be 8.817. Now what do? I add them all together. So if I add this, I'm going to get 10.8. Okay. 10.810. Is that pretty close to what we guesstimated? Yes. So now, if I ask you to look up at the periodic table and identify this element, what element has an average mass of 10.81? Boron. Number 5. Boron has an average mass of 10.811. Pretty close to what we got, right? If we would have had more significant figures, do you think we would have got exactly 10.811? Probably. So how do we feel about this process? Can we do it all on our own? Okay, so if you go to my website, on the right side of the screen in the homework section, I have put your homework for you. Okay, basically, it is only 4 questions. You have plenty of class time to get it done. My advice to you is read the question. Not every single one of these questions is asking you to do math. So make sure you understand what the question's asking you first. Answer the question. Don't just try to do the average atomic mass on every single one, okay?